In this video, we will be analyzing power and work related to shooting a basketball. We will be analyzing a free throw shot, a three-point shot, and a half-court shot, comparing the data between these three. The free throw shot has the least power of any shots because we are shooting it from the least distance. We filmed us taking a shot and put the video into Tracker to analyze the data. We can see the graph of the position in the x direction, which is a constant negative slope while in the air. This makes sense because air resistance is negligible. Secondly, we can see the graph of the position in the y direction, which looks similar to the actual travel of the ball because the ball goes up and then comes down because of gravity. We can see the graph of the velocity in the x direction here, which is a constant flat slope at about negative 3.6 meters per second. This also makes sense due to the constant negative slope of the x direction position graph. We can also see the velocity graph in the y direction, which is a constant negative slope downward. It travels quickly upward, stops for a split second, and makes its way down. We can see the graph of the acceleration in the x direction here as well. We can clearly see that the graph has zero acceleration because it is not accelerating in the x direction because wind resistance is negligible and it's in free fall. Finally, we can see the graph of acceleration in the y direction. This is pretty self-explanatory. The graph is a constant negative 10 meters per second squared, which is acceleration of gravity on the basketball.
We look at the calculations through the dynamics lens, including powers equal to work over time. We find the force of the ball by multiplying the mass of the ball by the acceleration it had after leaving his hands. We then multiply that force by the distance his arm moves for work. Then we finally find the power by dividing the work by the amount of time it took to move the ball, which resulted in 8.6 watts.
For the three-point shot, he is farther away from the basketball hoop, so it requires more work to get the ball into the hoop, which also requires more power. The graphs that Tracker provides for this shot are very similar looking, especially in slope, but the values are different. If you want to see for yourself, pause the video at each graph. This trend continues for the acceleration graphs as well.
For our three-point shot, we use the formulas of force, work, and power. For the three-point line, the force of the shot was 9.36 newtons. The work done on the basketball was 6.45 joules, and the power of the shooter was 21.5 watts.
And now for our half-court shot. As you can see here, the slow-mo is just so nice. And the celebration, even better. We'll do that one more time just to show off. The graphs, again, are similar to the ones in the past, but again, the magnitudes are just raised since the distance of the shot is increased.
Once again, the calculations are very similar.
Thank you guys for watching our video. Peace out from, A-Town.